All right, it says if you have 50 milliliters of 0.0125 molar acetic acid, what mass of sodium acetate should be added to make a buffer with a pH of 5.25? Assume no volume change. The pKa of acetic acid is 4.76 and the molar mass of sodium acetate is 82.03. So this question is a very complex one. All right, so let's go through it step by step. The first thing that we need to figure out is what concentration of acetate will make a buffer that has a pH of 5.25. Once we know the concentration, we then use the volume and the molar mass to find the grams of sodium acetate that should be added. So we're going to again use the Henderson-Hasselbalch equation as we've done several times before, which is pH equals pKa, not equals again, plus log concentration of base divided by concentration of acid, like so. So in this case, our base is our sodium acetate and our acid is our acetic acid. But in this case, the variable is the concentration of base. So we haven't solved one exactly like this before. So we need to plug in what we know. Well, we know the pKa, we know the pH, and we know the concentration of the acid. So the thing we don't know is the concentration of the base. So let's plug in what we know. Then we know that we want the pH to be 5.25. We know that the pKa is 4.76. So we know we're going to have to add more base than acid because the pH went up from the pKa, plus the log of concentration of base, which is sodium acetate. I'm just going to write it as base, so I don't have to write out sodium acetate every time, over the concentration of acid, which is 0.125 molar. All right, so first thing we want to do is subtract, and then I'm going to write it the other way, so the log's on this side. So we have the log of the concentration of base divided by the 0.125 molar. So we're going to subtract 4.76 from this side and subtract 4.76 from this side, equals 5.25 minus 4.76, which is 0.49. Now, just as we've done before in previous chapters, to get rid of the log, for example, when we were finding the pH, or specifically we were finding the concentration of H3O plus from the pH, we use the shift log, or 10 to the log, and we use 10 to the 0.49. So we take the inverse log of both sides. The inverse log of the log is nothing, so it's just the concentration of base divided by 0.125, okay? So this just cancels out the log. That's how we get rid of the log. And then we take 10 to the 0.49, and 10 to the 0.49 is 3.09. Then finally, we do the concentration of base times, multiply both sides by 0.125, multiply by 0.125, and when you do that, you find that the concentration of base should be equal to 0.386 molar. Okay, so this is how you would find this. Now, does that make sense? This base concentration is higher than the acid concentration. The pH is higher than the pKa. That seems to make sense. Now, we just have to do dimensional analysis. We know the concentration of sodium acetate, we know the volume of sodium acetate, and we know the molar mass of sodium acetate. So specifically, we want to convert the liters of this sodium acetate solution to moles of sodium acetate, and then to grams of sodium acetate, like so. All right, so liters, not milliliters. We want to make 50 milliliters, so 0.0500 liters of this solution times. Well, we know the molarity should be 0.386 molar, which means 0.386 moles in a liter. So for 1 liter of this solution, we should have 0.386 moles of sodium acetate. Then finally, we need to convert those moles to grams. So we should do, for every 1 mole of NaC2H3O2, it's going to be 82.03 grams of NaC2H3O2. So it's just basically a dimensional analysis problem from General Chemistry 1. And when you do the math, you get 1.58 grams of NaC2H3O2. All right, so this is the mass of sodium acetate that should be added to this solution. Chances are this would probably slightly change the volume, but to make the problem possible to solve, we assume no volume change.